hosted by Rick Ackermans. And Rick, I'll let you just take it away, introduce your panel, and have at it.
Welcome, everybody. So the panel that I'm doing is Where Does Time Go? Basically, what it is it has to do with all the many things that can cause latency in video, whether it be compressed video, uncompressed video. It's just, why does it take time? We've been dealing with this since the beginning of video, whether it's the way the scan works, whether it's interlacing, whether it's converting from interlace to progressive, whether it's data packet transfer times, whether it's the speed of light, propagation of microwaves, buffer time, memory clocking, all those fun things that cause there to be delay. We've seen it on many programs, whether it's compression delay, where you have the news anchor who asks a question and the reporter in the field sits there and nods for an extended period of time until they're able to answer. It can be very short periods of delay, which can cause timing problems, keying problems. In some cases, just a millisecond or even a nanosecond of timing delay can cause various problems. It causes lip sync. Obviously, it goes on and on and on and on with the various types of problems that can be caused by timing delay. So we just have a round table here of people, or maybe in this case, a 16:9 square, whatever it is of people, to discuss the various issues that go into latency. I do know there's a lot of people who don't understand what causes the latency. There are people out there who don't understand the problems of latency. So with that, I will take this title slide away. Who would like to start? Who would like to bring up issues? Let's do it this way. Let's start with the low delay stuff, like switching and timing. Let's avoid compression for the moment. That's another issue to itself. So dealing with switching and timing issues and what can be done to keep that. Who would like to start? I saw Ciro's hand up. Want to go, Ciro?
I was going to talk about compression, so maybe I'll defer to Andy.
Okay.
So I was going to start with the really lowest delay stuff, Rick, which is the speed of light in fiber, because I think at the end of the day, most of the other elements of latency that we're introducing into the chain have some degree of optimization available to us. The only, as we're moving, as my picture showed on the last talk I gave an hour ago, just to distributed production, where the concept is that, we're actually not geographically co-located, then the transit time between the locations is actually, becoming the dominant thing. And obviously, if you happen to be using satellite connectivity rather than fiber connectivity, that becomes a whole new issue. But sticking with fiber connectivity, basically, you can go in conventional current fiber 200 kilometers per millisecond. So you can do 1,000 kilometers, unidirectionally in a 10 millisecond window, in a 5 millisecond window. So that's actually not so bad for quite a lot of things. And also, as I think I mentioned a couple of VidTranses ago, one of the fiber technology guys that I know locally in the UK was talking to me about hollow fiber, which basically means the actual light is propagating in air or in lack of air rather than through the glass itself. So that actually takes you from 2 times 10 to the 8 to 3 times 10 to the 8 meters per second for the actual transit. But my proposition is that that's the only non-negotiable in what we're dealing with. Most of the other elements that we're going to touch on are things that you can actually fix or at least improve on. That's my starting point.
Okay. Alrighty. Let's go with Adi.
Thank you. I want to add to Andy. As I see it, latency is something that one need to engineer. You need to engineer that in your facility, just like what in Andy presentation. If you put network elements, switches, routers in between, you need to engineer the latency, because as you add more and more network hops, that adds latency. Once you go outside your facility, you need to be in control, or hopefully you need to be in control of that, and be assured the number of hops and the delay that each hop will add. Because you can do the mathematical calculation of the delay in terms of physics and distances, but each network element which is added adds a small portion of delay. And then if we get in something like congestion, then that explodes. It comes to a point that if you send two streams, different paths that are maybe the same distance, but going through different hops, you can get different results and different latency accordingly. I can share an example that I had a long time from Russia when I had to go over 20 miles from 2 points, but it went through 10 network elements and networks. Going over 4G was faster than going through a fiber because of the number of elements that were placed in between those 20 miles. So going back to what I said, engineering and understanding the engineering behind it, being aware of that is thing that you would then understand the problems of latency if they happen to be there.
Okay. Hey, who would like to go next? Okay, Sergio.
All right, I'd like to put things into context before we, dive into some of the nuances of where the latency come from. We first talked about, speed of light limitation, and we mentioned some metrics there. But to give a more tangible number, for example, would be if you ever go through satellite, that's 22,000 miles, right, on a geostationary orbit. Back and forth, now you added 600 milliseconds of latency. If you go across the ocean from the US to Europe or even further, you can get up to 7,000 miles easily, which is a third of going to the satellite. You still get a good 50 to 100 milliseconds of latency, which is very significant. On the other hand, there's latency that we introduced ourselves for buffering, for alignment, and those numbers are also on the order of many milliseconds, 50, 100, 300. So we need to put things into context. The video frames themselves, they're much smaller than that, and they're not in our world, in the world of at least RIST, they're not as relevant as the transport latency that we're mentioning in these few examples that we have. Also, the routers and hops, like Ari was mentioning, a router, even the lousiest router, a home router, will only introduce about 1 millisecond of latency because of its limited CPU horsepower. But that same home router, or even a high quality router under heavy load, can introduce 100 milliseconds of latency. So it's important to make the distinction. It's not the routers that introduce latency by themselves or the hops. Is when they're overloaded, when their CPU wasn't designed to carry the amount of megabits and they're pushed beyond their limit. That's it.
Okay, Ciro.
Okay, there's one thing I like to say is the more time you have to do a job, the better job you can do. So there's the parts that you can't do anything about, like Andy said, the speed of light, but the parts that have knobs to turn. And those are compression and the protocol. So you give me more time, I give you a better signal. You give me a crappy network, you give me time, I fix it for you. So that's when you start engineering it. That's when you start making trade-offs. In compression, there's the fundamental trade-off between video quality, bit rate, and latency. Pick two, the other one will suffer. So in protocol, it's the same thing. If I say, Ajay, give me, I'm going to give you a network, but I want to unplug the Ethernet briefly and plug it back. Can you design me something that will write that? And he's going to say yes. And how are you going to do that, Ajay? What are you going to add?
Add latency to fix that.
Add latency to fix that.
Yeah.
So that's when you start tweaking it, right? There's always a trade-off with the latency.
Okay. All righty. Oh, so go back to Sergio.
One more element that I think we should mention is in compression and decompression both. Often we overlook the fact that multi-threading and our ability to create more complex algorithms causes latency, because when you do multi-threading and I now have to create a really complicated video that you split apart, multiple CPUs handle it, they have to then be stitched back together. And the only way you can do that is adding latency to align them again. That happens both on compression and decompression.
Okay. Before we move on to some other things, and maybe we don't have people to talk about it, but some folks have, said, new methods, possibly getting away from a quote rasterized video. Is any of that a possibility on the horizon? I'll toss that one to Andy because he's talked about some newer technologies.
So I think that the challenge that we've got and this is coming up literally every week in various standards discussions is we're looking for compatibility with systems that have are effectively raster based. So until we break completely free in a solution design of needing full interoperability with a raster based system, then inevitably we are sticking with the process of actually allowing for compatibility with raster based systems. And that that's some of the elements that we can't get away from. Just to counter, I think one of the comments just made just now, I think some of the, what Eddie said, throw latency at something. I think some of the choices we make at some points in the system, not only is there a quality metric, but there's a cost metric as well. Because generally, if we throw more bandwidth at things, we can make things work quicker and better. And that's true for the way you can do compression. If you throw more bandwidth, you need to be less optimal in the way you do compression. Similarly in protection, so the protection mechanisms we're deploying, if you're using an ARQ technique, then inherently there is the to and fro transit times involved. If you're doing FEC, inherently there's buffering. If you're prepared to throw double bandwidth at something with 2022-7, which was mentioned, the diverse, you're actually delivering twice the bandwidth or you're consuming twice the bandwidth you need, but there is pretty well a zero latency impact on taking that choice, apart from equalizing the paths. So a lot of the decisions that we make in both compression and in transit involve a trade-off between what bandwidth we're prepared to provide for the solution versus the other parameters.
Okay, you mentioned ARQ, and we sort of previously agreed we were going to make this non-RISC centric because we got RISC Day tomorrow. But in terms of retransmission for packet loss, what kind of latencies on a transcontinental link are we looking at if you have to allow time for a packet to be resent, and what can be done to keep that down? I'll go Sergio, unless somebody else wants to take it.
Like I mentioned, transatlantic or transoceanic link can be on the order of 5,000 miles. So now your round trip time, which is the optimal separation of your retransmissions, becomes on the order of 20, 30, 50 milliseconds minimum, or 100. And then if you want to statistically recover all packets, you have to leave room on your buffer for 5 times that. So that becomes very expensive, right? Half a second of a total latency buffering you need to do a clean transmission over those long distances, from one part of the world to the other.
Okay, so was that I saw Ciro, but did I see Adi before that?
I don't know. We're going to say the same thing. Go ahead, Adi.
Well, everybody's saying the same thing, but usually going transatlantic, it depends on the type of network that you have. The physics are there, but usually going transatlantic, you will get like New York to London, it will be a retransmission will be about 70 milliseconds. So if you're doing 5 times ARQ, that would be 350, or the common number that usually people use is a buffering of 500 milliseconds. Of course, if you're doing London to Australia, you will have to then settle with a 1 second buffering and retransmissions to recover about 150 to 170. The problem goes back to the engineering. You never know where, or you should know, but you never know how is your packet being delivered. And the example of London to Australia is a very good one. You never know whether it's going through the sea, whether it's going through the UAE, Singapore, going through Russia. You never know that unless you prepaid for that path and you know and qualify the path. Reroutes are there that can happen anywhere. So the buffering, as Sergio said, is something that you need to accommodate to those reroutes or things that will happen while in transmission to cope with the problem. Now, I want to go back to what Andy said before about raster or not raster. When you take off the legacy, the raster base, the saving will be few milliseconds. But any hope, just like Sergio said, can add tens or to hundreds of milliseconds if it's not configured properly, doesn't have a correct queuing, or poor engineering. That is why a lot of companies putting their effort in doing that engineering in the provisioning of paths, in providing quality of service, queues, high priority, so that video will be delivered without any delay. And also keep in mind that now we are pushing more and more data through networks. 2110 gives us magnificent numbers of bandwidth that we need to take care of. This is no longer 10 megabits. We're talking about gigabits of traffic. Multiply that if you're doing 2110, sorry, if you're doing 2022-7, and then you want to do multi-cameras. That's a huge pressure on the network, and that engineering of network elements and quality of service, then it becomes more important. As we see the industry going forward with that, we will need the assistance of the network element manufacturers to take consideration into that, not only inside the facility, but also outside the facility. Recently, I saw a piece by Mr. Edwards, I think he's with us, I heard him before, about how AWS is dealing with routing traffic inside the AWS or any cloud environment, in which you need to design those paths. How do they go inside? Because once you go to a cloud, you hand off your signal to somebody else to engineer, and we hope that he's doing the proper job doing that, taking care of balancing and so on. Sorry for the speech.
All righty. All right, let's move. Is that a hand, Ciro? I wanted to move on to compression. We got 4
Yeah,
minutes.
no, go ahead. Go ahead.
Okay. All right. So as we wrap up, because we have 4.5 minutes left, let's talk about the real time waster, compression. Anybody want to dive into that?
I'll talk about compression.
Okay, we'll go Ciro, then Andy.
Okay. Well, it's back to that thing, right? If you give me time, I give you a better job. So if I can look into the future, I can compress it better. So, but the future is not here, so I gotta wait for it. So that's your latency right there. If you hobble my encode and say, no, I want low latency from you, I only can look at the past. So, but you can with techniques like AVCI, even in the 264 times, or what is being doing in ultra low latency HEVC, you can get sub-frame latency. You're just going to have to pay for it with a little bit more bandwidth to keep your quality. But you can do very basically tens of 5-10 millisecond latency on an encoder and have very good quality. Just pump up the bit rate. That's what we're doing with low latency, ultra low latency HEVC.
Okay. I think radio cameras for sports events are a good example of where latency has been really optimized within the live production workflow. What I was going to say is, in terms of compression, JPEG XS has obviously come on the field in the last couple of years. We've been using it extensively, and because the complete encode decode delay is well sub-millisecond, it's negligible. And typically, for what I call tier 1 broadcasting, we're maybe doing 8:1 compression ratio on that. So it's nothing like a temporal compression, but it actually gives very, very low latency. But one interesting anecdote on that: a lot of people are presenting video in as quad 3G, presented as quadrants. And if you do that, inherently, because of the way you need to wait to get the data in, you actually are incurring a whole half a frame delay just because of the way you're choosing to interface. So there are some gotchas in the system. If you analyze overall latency, you may have the tiniest compression latency, but then suddenly, literally, the way you actually interface your signal can actually cost you a significant amount of time. So it's worth being aware of the whole chain of what you're doing.
Okay. 2-minute warning. Anybody else? Go, Ciro.
Motion JPEG is an extreme of that. The same thing I did. If you don't want, or you can't look at the past or the future, then you get very, 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 very low latency, but you pay for it with bandwidth.
Okay. And just a couple comments. These are more comments than things, but we have a comment from Dr. Yendo Hu. And it says, in reality, latency is constantly changing, frequently done through networks, codec systems. How can this be addressed? Okay, anybody got okay, so how can latency be addressed? You got 20 seconds.
Can I take it?
Yeah, go ahead, Adi.
A way to take care of latency is to look to the past, beyond the 20th century. Let's go to the 19th century. How mail post was working. If you recall, in the US, there was a bunch of new kids doing the Pony Express. What they did, instead of riding a coach from one coast to the other, they put a bunch of endpoints. Every time there was one pony riding to a place, changing horses, giving him the message, and they reduced the time of messaging from 1 week to a day and a half. If we can put hops, smart hops, that can provide delivery, ARQ by way of wrist or whatever, propagate the data forward and take care of what is missing, that can reduce the overall latency by a factor of 2 to about 3 than what is done today. Having smart hops can solve that problem, just like the guys from the Pony Express did.
Okay. Okay, we are out of time. But I will just also want to mention that Ali just said he got a RTT of 210 milliseconds from his home in Turkey to UCLA. And on that note, we have come to the end of our time. Thank you very much, everybody.